All right. So now we have with us Laura Villafañe. She's also assistant professor at the same department as Francesco, space engineering at the University of Illinois at Urbana-Champaign. She has research on turbulence, multi-phase flows, and development of experimental diagnosis and data analysis tools to study complex fluid mechanics problems. And she's a space engineer, and she did a PhD in the von Karman Institute, and then she moved to the United States, Stanford, and then in Urbana, right? Mm-hmm. So thank you very much for being here, and the floor is yours.
Okay. So hello everyone, thanks so much for the introduction and for hosting us. So it's really a pleasure to pass by Spain year after year for Christmas, right? So we are like el turrón. And so this time we have the honor of being here with you, presenting you some of our work. So thanks so much for being here, listening to us, and for the invitation. So today I'm not burning things. I don't do barbecues in the way that Francesco does with material and stuff like that. We're going to be talking about particle-laden flows. So this talk is a bit general. I'm going to be actually showing you 2 mini stories. I'm going to try to fit in a short amount of time 2 mini stories of ongoing work. And the main item of the agenda, so if you go out with one thing from here, is basically I want to make you think of fluid problems from a slightly different perspective. And it's the fact that all flows that we have around us have particles. So this is a very crowded slide, but if you think about the air you breathe, and no, I'm not going to talk about COVID, but I could, but volcanoes, the atmosphere, rivers, pollution, right? All those are examples of flows and that are not free of particles, unfortunately, in most cases. Most cases are also turbulent. So the reason why you might want to take the presence of particles into account actually depends on the application, right? What is your end goal? So if you are interested with combustion or industrial processes, looking at how those particles are spatially distributed, which is generally non-homogeneously, will be important for you because that will determine the efficiency, right, of the combustion processes, for example. And you might want to also track the evolution of these non-uniformities of particle distributions in time and in space, because that will tell you about, heat transfer, modeling of heat transfer processes, right? How these dense regions of particles evolve in time and in space. If you are, why we need all this? Well, let me put you this up front. Why we need all this is that if you think about the fluid dynamic perspective of modeling particle-laden flows, the presence of particles modifies the flow. So you need to really solve the couple of equations of motions of the particle and the fluid. So as you increase the number of particles, if someone of you does modeling, you can think that this gets extremely expensive and in most cases unaffordable, right? So we need simplified models, stochastic models, to be able to introduce what is the effect of the particles for heat transfer, for modulation of the turbulence and things like that. Also, if you are, for instance, in operations in sandy environments, the presence of particles you might want to care about because it compromises the mission, right? So both in terms of visibility or in terms of damaging components. So we'll talk a bit about that. So with this very short background, I'm going to be trying to sweep in 2 stories. The first one deals about how do we define actually what is a cluster of particles, right? And how do we track it on time and in space? So that's in turbulence. So that's the first part. And the second one is totally different. It's more applied. And here we're going to be talking about a supersonic jet that impinges on a surface and creates a a cloud of particles, right? So the reason why you might care about that, for instance, is if you are landing on the surface of a planetary body and you are creating a huge cloud of particles that goes very fast away from the impingement point. So here we have 2 images of particles in turbulence, and you can think that the background turbulence of the flow might be exactly the same, but in one case you see something like in the right, and in another one something like in the left, right? So this is an instantaneous snapshot of a dirty environment, call it like that if you want. So what is the difference between the right and the left? So the flow you would think to be the same. The only thing that might be different is the particles, right? So when we have something like in the right or in the left, mainly depends on a non-dimensional number, which is the Stokes number, which is another thing that the ratio of the time constant of the particles, so the inertia of a particle with respect to the inertia of the flow at some representative scale that is important for your problem. So if the Stokes number is very, very small, like 0, right? So there we are in a situation that we have a tracer. So this is the particles that you want if you do particle image velocimetry, for instance, those of you that do experiments. You want your particles to follow exactly the flow. So if you put them in there, filling all the space, they are going to be showing, exhibiting random uniform distribution, right? So like in the left. If your particles, imagine that are very big, right, are ballistic at the end of the day. So they don't really care about what the flow is doing, and you will end up with the same random distribution. Now, anyway, in the middle, Stokes number order 1, 10, the particles will be able to follow some of the flow fluctuations, but not all of them. So that results on what we call preferential concentration, which is the picture in the right. And I mean, mechanistically, you can think about that the particles are ejected from vortex cores and tend to accumulate in regions of strain. So we have a picture like in the right. And this is what happens in most cases, okay? So now, there are many things we might wanna look in here. The main thing I'm gonna talk about quickly is that we wanna know how big, we wanna be able to determine the shape and size of those structures and how they change over time. Why is that? Well, imagine, for instance, that you are getting radiation from the left in that picture, right? In this case, it will be the same, it will be the transmission of radiation or the heating will be the same all over the place, right? But in that one, it really depends where it passes through, that you're gonna have a fluctuation of radiation transmission or a fluctuation of heat transfer in space. So you are modulating all these things, and the macroscopic characteristics of these structures are actually what will determine how you are modulating your heat transfer or your flow. So how we study this, very quickly, we have built this new facility in our Illinois. It's actually, was a very hard work to do. Let's say it's as tall as the building, so that's one of the things. So it goes 4 stories from the roof, from the ceiling to the basement. So it's the longest, as far as I know, that exists around. So it's a vertical channel flow facility, canonical turbulent experiments with particles. So it's very flexible. We can vary everything: Reynolds number, particles, heat transfer, electrostatics. We still have to exploit it. It's just recently being built, but this is what the type of wind tunnel that we use to study canonically these particle-laden flows. We can look into modulation of the turbulence, which is in the left, or the structures of the particles, how they evolve, which is what we are going to be talking today. So the first, let me show you these 3 images. So those are one image of particles for 3 different cases. What is different in here? Those are experimental images. We have the same particles, so same are solid nickel particles, 12 microns small. There are inertial deviate, this Stokes regime where they do preferentially concentrate, and we vary the flow. Remember that the Stokes depends on the flow and on the particles, right? So you can change the number in one way or in the other one. So 3 different velocities, 3 different Reynolds numbers, and 3 different Stokes, 5, 12, and 31. So which one is which, right? They have the same, more or less. I mean, the picture that I took from the left, from the top one, looks like has less particles. Well, bad luck on the one I chose, but the loading is the same in all of them. So how do we quantify preferential concentration? So one way of doing the most classical and simple one is do box counting, which basically you choose a box size, count number of particles per boxes, you get an histogram compared to a random, and you can build an index of preferential concentration, like you see there, which depends on your box size, L. And you can do this for all box sizes, and you get something like this. This is a general number, let's say, put it that way. You get one number. Doesn't tell you anything about the size, shape, or anything. But you get that as you increase the Stokes number, so increasing the Reynolds number, the clusters are more like diffuse, right? So if you look to the last image and you compare it to the previous one, structures look the same, but the particles are less concentrated together in the skeleton of the cluster. So fine, we have one. Now we want to say the sizes, again, sizes, define clusters and see the morphology. The most classical way we've been doing this is actually using Boronoid tessellations. So Boronoid is a unique decomposition of the space in which every cell will have only one particle, and the sizes of the cells that you get are inversely proportional to the concentration. The smaller the size, the more particles you have together. So we can do this and connect the cells together and basically define these clusters, right? So this is the most used way to define the clusters. Once you do that, you can actually run this through all the thousands of images that you have and build a PDF of cluster sizes, which is what I'm showing in here for the 3 Reynolds numbers. And there is many fluid dynamics that we can comment in this one single picture. I'm going to skip this for now because the point I want to highlight in here, one thing that we've been doing actually was started by a master student from Spain that was working with me for 1 year at UC, and he started doing this, which is actually a remedy to say we can do this Boronoid tessellation and then do it over thousands of images, and if you want to do it in time, do it over thousands of time steps. Now, this is going to be a very costly and time-consuming process because as you increase the number of particles, this scales very badly. So one thing that he started doing is saying, okay, so Bose counting methods for here is very bad. Also, you think about it as you decrease the number of particles, you have too few particles, how do you define a spatial distribution of that? Boronoid is very expensive. So he basically came at me and said, can we use the fact that in reality particles are discrete? And this is a very standing problem in particle-laden flows. Particles are a discrete field. It's not a continuous field as the fluid, right? So can we stay on the discrete field and not try to do a map of concentrations and use density-based clustering algorithms that are usually used in CS to analyze and classify different large amounts of data, right? So we went to that route and we used a method called a DBScan. And I'm going to skip all the details in here, we can discuss further. But what we did was to develop the method, apply DBScan to a large data set of DNS simulations with Lagrangian point particle models. So we have like 2,000 snapshots on a 3D domain. In total, per each snapshot, so the 3D, we have 4 million particles, 2.9 million particles identified as clusters, so this is very expensive. So we ran our DBScan algorithm that is a function of 2 parameters, epsilon and minimum number of points. So actually what we do is to go through all the particles and we look in a radius epsilon if that particle has a minimum number of points within the surrounding. If it is, it's defined as a cluster particle. If it is not cluster particle, all to the nest. So this part is a bit expensive, but you only need to do it once. And we determine the parameters based on the information of the number density and so on of the data set, so there is no user input parameters, which is what we want to have, right? A robust method. So this is an example of what we get. Blue are identified particles that are clustered, and orange are particles that are identified as not clustered. I show you only a 2D projection of it. So, of course, this is a new method. We need to compare it with something. We need to be sure that that makes sense. So we are comparing to the standard, which is Boronoid, which is the expensive one, but okay, fine. So what you're seeing in here is actually the PDF probability distribution function of cluster volumes. The red are the Boronoid, so the trusted gold standard, and the black are our results from the DBScan. So our clusters, to be sincere, are a bit bigger, fatter, and that's the fact that we impose a radius epsilon around the particle, so they get to be a bit fatter, but the scales are the same, basically, right? We have a matching in both cases. We have a power law for the distribution of sizes of clusters. The good thing about it is actually when you go to the plot in the right, which we are showing the cost saving that we are finding with this. And it's like 16 times cheaper to do the DBScan on the same data set than to do the Boronoid. So if you need now to do this in many time correlated snapshots, this is going to be a nicer way to go. So we did this because we were looking for tracking, really. We wanted to see how these structures change on time. And then one step to do further, that we are still getting there, is actually correlated to the flow and try to understand what causes what. So the tracking was the end product. So now what we do with this, and this is where the saving really comes, is that we have our 3D cluster. And now we want to do the same thing in the same snapshot, so we have our 3D cluster, and we need to connect one to the other one and see how it moved, and which cluster broke, and where did the particle go. So what we do for that is we do tracking, actually we split it in 2D. We will do it in 3D, but it's just simpler. We have our 3D structure projected in 2D planes, 2D slices, And now, in each 2D slices, we simplify further the topology, because we don't really need to track all particles if we want to track them, only just the representative ones of the cluster. So we define a series of boundary points and skeleton points, as shown in the figure in the right and the top, and we only look for topological tracking of each of the skeleton points that we have there in the right. So we are simplifying tremendously the problem, but if you want the macro scale, that's all we need. So yeah, for each point between different time steps, we actually do a topological mapping, follow the particle skeletons, and basically are correlated. The boundary need to not have changed too much. And if we do this through all the times and all the particles, we can know absolutely everything of which particle moved to which other cluster, so actually analyze the events on the clusters. So this is just some examples, things that we can look at. So we can look at what is the most probable cause of birth and of death of a cluster, right? So we see, and this is just probability maps of things. So we see that the clusters, the most probable birth event of clusters is that they dissociate from a larger cluster. So a cluster breaks up into smaller ones, and they die when they merge together with another one. And we can also analyze their lifetime, which ones live long, and how and why they break. So one of the things that we want to do with these things is basically analyze time scales, so see how long do they live, right? And then the next step that I'm not going to talk about today is basically what's happening in the flow behind it when this event happens, right? So this is for all the clusters that were born and died in domain, the PDF of the lifetime. So we see that we have some very large clusters of the order of the convective time scales that actually are those. Now we can see through all this analysis that those die slowly by disintegration. So it's a large structure that goes slowly losing particles. And we have some short-lived events that are just merging and changing particles in here. Anyway, I'm going to switch dramatically tracks in here to the second topic, which is supersonic impingement on granular surface. If you look to landing 2020 Mars mission Perseverance, there was a picture in the introduction, but I didn't highlight it. There were particles all over the way. Perseverance didn't land on the surface of Mars with a rocket, right? There was a descent crane, and still so you see particles all over the place. In the moon, there's no atmosphere. Apollo missions landed with a rocket, right? Now, there is totally different phenomena that happens when you have a supersonic jet impinging on a surface in these two cases. It's a complex thing to land humans and heavy loads on the surface of Mars because due to the terrain and also the fact that there is an atmosphere, which is, well, different than on Earth, but much more similar to Earth than in the moon, what happens is that you will do a huge crater down, so you will make a hole as you are landing, and you will shoot particles all over the place. So this is a very important topic for NASA now, so NASA is actually part in this fine of the project, which is how do we even get to predict this problem. So here we have a transient problem, so supersonic jet, granular surface, you form a crater, particles are dispersed all over the way, high-speed particles near the surface, so wall jets that reach hypersonic speeds can get to orbit, if you are nearby, well, you don't want to be nearby, you get sun-blasted. And you go from subsonic to supersonic rarefied, dilute, high loading in a matter of seconds, right? So our modeling tools are struggling to get to this type of all mixtures of regimes, and there is also no data for this type of situations, because experiments are quite challenging. So just for as an example, you can see in the right two images, the top one is for the Apollo 15 camera, and the same thing you can see for all Apollo landings. You basically see that you don't see, right? So you don't know where you are landing, and you might end up, like in the Apollo 15 happened, over a crater. This wasn't a crater formed by the lander, it was a crater that was there already, but you can land in a place that you didn't envision and be a bit tilted, and basically for the Apollo 15 it was 1 degree away from being a critical failure. So you really would like to know where you are landing, let's put it that way. So how we do this? We are actually replicating, somehow we cannot get rid of gravity, right? It would be super cool to do these experiments under no gravity, but so far we are doing it in the lab. So we have a vacuum chamber where the main takeaway in here is that we have a vacuum chamber, so we do a reduced ambient pressure environment. We have a thruster, so a nozzle, Mach 5 that replicates exactly the same conditions, aerodynamic parameters of the landers. We are able to vary the surface, the distance of the nozzle to the surface, the granular material, and for now, some of the results that I'm going to be showing you are actually for the same stagnation conditions, same Mach 5 under-expanded jet, and the only thing we vary is the ambient pressure. So do we do vacuum up to Mars conditions, which is around 800 pascals, or we go down all the way to lunar conditions, which is about 6.7 pascals. So by doing that, what you are actually varying is the jet expansion ratio. So in the lunar case, you will have a very under-expanded jet, right, with a high opening. On the Mars condition is more collimated, but still under-expanded. So whatever happens on the granular material happens because the flow forces it, right? So the first thing that we need to know to be able to analyze the results is what is the flow doing in both cases. And one reason why this is interesting is because it's dramatically different, the dynamics of what's happening for a jet expansion ratio around 300, which is the lunar, or at 2.84, which is the Mars. So here I'm showing you center wall pressures on a stagnation plate, so there are no particles here, as a function of distance to the surface on the horizontal axis. So one thing that is important if you think about the landing, we are doing it at steady conditions, but when you are landing, you are going from the right-hand side of this plot to the left. You are moving to the surface of the ground, decreasing distances, right? And if you are in the moon, what is happening right below you is that the surface pressure is increasing as you approach the ground. Make sense? Now, if you do the same thing in a Martian environment, the pressure first increases, then drops, and then increases again. That's kind of important because it just means that you are overloading the regolith, the surface, twice, right? So you will be changing totally the dynamics of the cratering, and you have two peaks of pressure as you approach. So we did a lot of measurements here. We covered the full parameter space using synchronized high pressure and slurring. And the reason for this behavior of the surface pressure is that while in the lunar case, those images are a bit dark, but probably you see for 4 distances, I'm showing only, the flow structure is the same. You just have a curved choke and radial jet, but it's the same. It doesn't change it. If you do this for the Martian case, you actually can find 3 types of flow configurations. Up to 4 non-dimensional nozzle distances, you have a surface shock. This is totally dark. But if you believe me, in the image of the middle, you see a Mach disk that changes the distance to the surface as you vary from 4 to 8 diameters. And if you go farther away than 8 diameters, you transition to an oblique shock type of flow structure in which you have you are increasing the dynamic pressure in the axial direction and overloading the surface. So that's why the dynamics are so different for both cases. So very quickly to something that I find very cool. I told you that there are really few experiments in here. NASA is doing a lot of experiments now. It did it on the 70s, and they are putting a lot of effort now. But what they do is half-space, what they call half-space experiments. The reason is that when you have a lot of particles, you don't see anything. If you don't see anything, it's very difficult that you can measure anything. So they put a splitter plate at the center plane of the nozzle. Sure, you are modifying the flow. You have a boundary layer now that forms at the other side of the plate, but at least you kind of cut the crater in 2, and you can see at the other side, right? Okay, so we didn't want to do that. So we went to the full 3D and we said, sure, we can measure even if it's very opaque. So the first thing we tried, I was intended, as we wrote in the proposal, was to do optical attenuation-based techniques. Very simple put, it's like you have a laser and you have a photodiode. Light goes through. When the light's attenuated, it's because you have particles in the middle. You can correlate the degree of attenuation to the amount of particles you have. So we tried that. We blow the jet, we put the particles in the vacuum chamber, and we got no signal. So what's happening is that the amount of particles is so large that you are totally attenuating the light. No wall. So then, actually, NASA suggested that to decrease the amount of particles and so on, so basically just faking it. And we really wanted to do the real thing. So we thought a bit on here and said, well, you know, how much the light is attenuated depends on the wavelength of the light, right? So if you go from the visible 2 millimeter wave, so the amount of light transmitted on that range is much higher, so the extinction is much lower. So you can actually, not gonna get into the detail, but you can do transmittance plots in here, transmittance versus number density, path integrated. So the dash line, dot dash line corresponds to the visible, so a red laser, 650 nanometers. If you do the same thing on the millimeter wave, is the dash line in the top. So the transmittance is much higher. Now this is not very sensitive, so we went one step further, and we use the property that the fact that there is a phase shift of millimeter waves as they pass through a medium that has particles in the middle, and that's because you are changing the dielectric constant of the medium. Now it's air, before was air, now you have air, a mixture of air of particles, so the dielectric constant is different, so there is a frequency shift. So the important thing, skipping the math in here, is that your frequency shift, right in that equation, is proportional for a given particle material to the path integrated concentration of particles. So if you measure the shift, you can know the volume loading of particles that are in the middle. Sure, it's a line integrated measurement, but remember that you cannot measure anything, so it's better. So we actually tried this. This is the setup. It's actually a high resolve, temporal resolve measurement, so we are doing it at 10 kilohertz. We could push it at 20 kilohertz. Depends on how much you spend on your radar system. So we have in there basically the blue box in there is with a protection casing for the particles. It's our emitter and receiver, and we emit a chirp of millimeter waves that reflects on one, which is the reflector, and goes back as we blow the nozzle and form the crater. So I'm running a bit of time, but let me show you what happens for the two pressures. So we fix the distance here is relatively far, 15 nozzle diameters, and the images are very dark, unfortunately. Switch off the light, so hopefully you see something, but in the left, you're gonna see a video camera from the outside of the vacuum chamber, and in the right, time track measurement of this millimeter wave translated already to concentration. So for Martian, probably you saw something in there. Anyway, you have a very big fan of particles to the side, so there is an initial surge of particles being ejected, as you see there. Then it stabilizes. The dimension tests are 1 second, so after 1 second we close the flow and the particles settle down. If we do the same thing for the lunar, which that you don't see, so believe me, what happens in here is you have a small cloud of particles that is very near the surface, right? And it's kind of steady there. There is not the abrupt eruption as we saw in Mars. And this is what you see in the plot. It starts kind of steady, and at some point it rises up. So what did all that mean? So we are in the process of, well, by the way, the levels of concentration that you reach in one and in the other one is very different. So remember what I told you, that if we were to land a heavy payload in the surface of Mars, this will be a chaos, right, compared to the one of the moon. So you can actually see the orders of magnitude of difference of ejecta in one condition or in the other one. So interpretation of what is going on in here, well, everything comes from the, it's a pity that you cannot see the images here, but everything comes from the shock, the flow structure, right? At least at the very first milliseconds when the impingement, before the crater forms very deep, everything depends on the flow, is dominated by the flow. So here, for the Martian condition, this surge is due to the fact that we have oblique shocks impinging, not really at the impingement, but at the sides, right? And so it's a very violent eruptive erosion in which you actually liquefied the soil. And you can even see, if you process the images, you can see small bubbles of air that grow from the inside to the outside. So you have liquefaction. If you look to the same thing in the lunar, you don't have this strong impingement because remember there is a surface shock, right? So it's kind of protecting the soil. But what I didn't tell you, why we start by a steady erosion and then somehow we transition to another sort of another mechanism of erosion, is that our vacuum chamber is small, and that is something we cannot do much about unless someone wants to make a donation for a huge vacuum chamber. And if you are putting air in a vacuum chamber, of course you are changing the ambient pressure. For the lunar case, the pressure is much lower, so the effect is significant, while for Martian, it doesn't really matter. So we start by a wide surface shock, but if you follow those images. In the third one, you will see that actually we are having cell contraction. So at some point, there are oblique shocks that impinging on the surface, and that's what we believe is when the surge of particles happens again. So we are changing the erosion mechanism there. In any case, for the first times of the test, this is highly representative. Okay, I think I went kind of over time in here. So in conclusion, basically, I kind of show you a new method, hopefully sell it as more efficient, computationally more efficient. We need to exploit it now to correlate with the flow dynamics, but it's something that we couldn't do otherwise with the existing methodologies. And the second one, well, I mean, I hope I show you that it's very exciting to blow up particles in a vacuum chamber. It's also very painful to clean, but this is an ongoing project. If you invite me next year in here, you probably see results of crater formations and some other BLIF. We are doing BLIF for also measuring the flow velocities in the presence of particles, so stay tuned on that. I'm gonna just leave it here with a slice of the people that is actually making this possible, people like you, and some other projects that we are doing in here. There are many more things ongoing, so we will be talking to you for hours. So I'm gonna stop it here. Thank you.